So good morning, everybody. Thank you for joining us. My name is Esti Hudis, and I help coordinate the Methods Core seminar series. And this is actually a joint presentation with two other cores at CAPS. So this morning, Steve Gregorich is going to present the second of his three-part series, and today's topic is Introduction to SAS PROC VARCLUS, a mostly superior alternative to EFA. Now, Steve probably needs no introduction, but I'm going to say a few words. Steve received his BA in psychology and Ph.D. in quantitative psychology from the University of Texas in Austin. Lucky for us, he decided to leave Texas and come to UCSF. And just as a side, two of my favorite UCSF practicing statisticians received their PhD in psychology from Texas, and the other one will remain nameless. Okay, so Steve has been a revered colleague in spite of the fact that he uses SAS and not Stata as his main or only possibly statistical software. And as a side thing, I have to tell you, I received the morning update from the New York Times, and SAS started advertising in that venue. There was an advertising from SAS at yesterday's morning, the morning, which I can share if there is time. Okay, so Steve is in the Department of Medicine, and he has a lot of interests, and some of them is, of course, working with the models that he's going to describe to us today. And the last thing I wanted to say is that we at CAPS and more broadly at UCSF and beyond have been very lucky to be able to benefit from Steve's statistical intuition, knowledge, and generosity. We hate to see you going, Steve, retiring, I know, but I appreciate very much your offer to present this second of the three seminar series before retiring in a few months. And I forgot to check with you, Steve. Did you want people to ask while you're presenting, and do you want them to put it in the chat or just raise hands or what?
Well, so it's fine with me. I might be so busy talking
Rachel and I can monitor the chat.
If people want to put stuff in the chat, or if it's too hard to write in a chat, some questions are just easier to say than to write, and so
just raise your hand.
Just raise your virtual hand or your actual hand if you think someone's looking at your video feed, and then we can stop, because this is perhaps not familiar territory for a lot of people, so it's probably more useful to ask questions as they arise, and that's fine. We should have plenty of time for that.
Okay.
I'm just going to pop in real quick here too, for a moment. Rochelle, I'm the coordinator, and let you know if you have not received the handouts for today's session, I am emailing them to you now. So check your email. If you have not already received them, you'll be getting something from me in the next minute or so.
Thanks, Rochelle.
Thanks. On a Zoom presentation, the handouts might work on the screen. They would never work in a regular kind of presentation in a room, but I'm going to put them up on the screen when I'm talking about them as well. But if it's more useful for you to look at your copy, then that's totally fine. Are we ready? Okay, so apparently when I share my screen like this, some people see a kind of a small image. and I don't have as the presenter, I can't see the options. So Rochelle, if you could explain to people if they are having a small image, what they can do to fix it.
Sure. So now while Steve is sharing, it should be at the top of your screen, but it might be on the side. There's a bar that says you're viewing Steve Gregorich's screen, and next to that is another bar that says view options. So if you click on view options, at the top it should say zoom ratio, and you can adjust the size of what you are seeing using that zoom ratio. So you can move it up to 150%, etc.
Okay. All right. So we'll get started. So this is a second part of a talk on basically exploratory methods for psychometrics. And the genesis, this is a talk I've given before. I gave this talk at CAPS a decade ago, probably, and I've given it other times around UCSF as well. But Tor and the visiting professors group wanted a presentation on exploratory factor analysis, which I gave last month. But I also said that if I'm going to present on exploratory factor analysis, then I really want to present on SAS PROC VARCLUS, because I hardly use exploratory factor analysis. I don't use it primarily. I do use it, but if I have a big item set that I need to conduct some kind of exploratory analysis to try to understand the latent structure, I will use PROC VARCLUS first. If it's a small item set, I might just start with exploratory factor analysis. But there's a lot of reasons for my preference for VARCLUS, especially with large item sets, and I'll talk about that. So a lot of the slides, a lot of the first 5 or 6 slides that I am going to provide are identical to what I provided a month ago, but I just thought that some people might not have seen the EFA talk, and so I wanted to provide a little background. And so the slides, the first couple of slides are ones that I've used before as an intro to VARCLUS and as an intro to EFA, so they kind of work both ways. As soon as we get through the background, I'll do an introduction to VARCLUS, and then I've got 3 worked examples. The worked examples represent different eras of my familiarity with VARCLUS, and I'll kind of explain some of the things I was doing with VARCLUS in the earlier days that I might not do these days, just to try to draw some contrast there. And then because I know how to fit confirmatory factor analysis models, I always, after I find a VARCLUS solution that I'm happy with, I always follow it up with a confirmatory factor analysis model. A lot of times with a large item set, you're going to end up with a second order factor structure, and I'll talk more about that as well. VARCLUS doesn't have a whole lot of tools. It has some tools for assessing how well the clusters that it suggests explain the data, but something like confirmatory factor analysis has a more robust and recognized set of tools for assessing model fit, and so that's why I go with that. So the common factor model, I just want to talk generally about that, and you can think about this as like factor analysis. What we often have is in science is some kind of indirect observation, and it's just because constructs are not always directly observable. They might be impossible to directly observe, like an attitude or a personality dimension. But some things are just not observable because they're, say, sensitive behaviors, and so you rely on self-report, retrospective self-report. But I do want to emphasize that indirect observation is something that's part of most sciences. It's in economics, it's in physics, it's in chemistry, if you're in the right kind of chemistry. So it's not something that is unique to kind of behavioral research. Sometimes indirectly measured constructs, especially in the behavioral sciences, are called latent variables. And again, they're everywhere in science. And in some cases, latent variables are identified by multiple fallible observed variables. So you basically have a lot of measures that are not quite exactly measuring what you're after, but they're related. And you hope that by measuring multiple kind of semi representative variables for the construct of interest, that you'll get a good bead on the construct of interest itself. Sometimes in other sciences, latent variables are just inferred from what is observable, but in a different way. So if you're working in like radiochemistry, you might shoot a particle beam at a target, and you're going to look at the particles that fly off of that target, as well as the energy released, and infer what new element might have been there for a billionth of a nanosecond somewhere along the way. It's a different approach to indirect observation. But here we're interested in having multiple measures that are, none of which are perfect representations of what we're trying to measure, and amassing that information to our advantage. So a measurement model then relates a latent variable to these manifest or observed variables. And the idea is that the latent variables, say it's an attitude or your intelligence, those latent variables are hypothesized to directly cause responses to corresponding manifest variables. So if you ask someone a series of questions about an attitude, the thought is that it's their kind of mental positioning on some kind of dimension of a particular attitude that's going to cause them to agree or disagree with the question that's posed to them. And that's the whole idea. So it's a causal model. If you have multiple manifest variables per latent variable, then this measurement model can be empirically evaluated via a common factor analysis. And the word common here basically refers to the fact that in factor analysis, what's of interest is the variation that's shared across a set of items or responses to a set of items. Each item might have some unique variation that is not shared with the other items. And that's just unique variation that can't be part of the hypothesized latent variable that is believed to be causing responses to the individual items. So the focus is on the shared variation between a set of items, or in other words, the common variation. And so that's the whole idea behind that label of common factor model. And the idea here is, if you've got a set of items, you believe the set of items are indirect measures of a smaller set of latent variables, and what you want is some evidence that your variables do in fact represent and measure the latent variables of interest. And so if you can fit a common factor model that so you have a hypothesized clustering of items that belong to one latent variable, another set of items that correspond with a second latent variable, etc. If you can fit a model that basically supports that clustering of items, and the relationships between the items and their corresponding latent variables are fairly strong, then that's evidence that your items or your instrument measures what you say it measures, because the clustering of items and the relationships between items and latent variables aligns with your theory. And so that is a form of construct validity. You can also use a factor analysis to have a more parsimonious representation of your multiple observed variables, and it can provide empirical justification for creating composite scores or scale scores, which are more reliable than the individual items. So just some ideas on some broad goals of all of this. So this is just a conceptual example of something in economics. If I want to measure 2 dimensions of consumer confidence, and these I think are the actual items that are used to measure consumer confidence. So you're listening to the news and they're talking about consumer confidence is up or down. It's based upon this kind of questioning. So they survey people and they ask them about their expectations for what's going to be happening in the business climate in 6 months. So they ask about business conditions, employment, and income generally. And then there's questions about personal purchase plans. And they ask about kind of big ticket items. So people answer these questions. And the idea is that there's 2 latent variables that are represented by these 6 items. Expectations and plans to buy. And so if you think about this as a common factor model, we've got our 2 latent variables in the ovals. Each is hypothesized to cause the responses to corresponding 3 items. And these are these kind of straight arrows. So the idea is that expectations, latent variable in a person's mind, causes their response to the business expectations 6 months from now question, and the same for employment, and same for income. And the same thing holds for personal plans to buy. And this double-headed curved arrow shows that these 2 latent variables are probably correlated, and the model can estimate that correlation as well. So what you're going to get is often these effects are represented as standardized regression coefficients. And in some simple cases, they're basically the same as correlation coefficients. And then you can get a correlation coefficient or covariance for the relationship between the 2 latent variables. And so this is just a made-up example, but you might estimate all of the correlations between each item and the 2 factors. And if you found a kind of a pattern like this, it would suggest that these 3 items are related to expectations, but not so much related to individual purchase plans, and the opposite holding here. So if you got a pattern like this, it would suggest that the 3 questions, the first 3 questions about 6 months into the future, your expectations, that those are clustering together, and they seem to share a common concept or construct. And the same thing with the last 3 questions. They tend to cluster together, and they seem to be fairly strongly related to and kind of an overall construct. But all of these kind of cross-loadings, they're often called, are pretty low. So there's a good distinction between these 2 sets of 3 items. So if you received a result like this, it would be some evidence that your theoretical expectation of I want to measure something about future expectations, so I created these 3 items for business, employment, and income. And I also wanted to measure something about personal plans to buy that's related to consumer confidence. So I've got auto, house, major appliance. If you got a result like this, it would help to bolster the idea that your first 3 items are really interrelated in a way, and the second 3 as well. And when you look at the item content, you can come up with labels like this, expectations or plans to buy, that maybe your colleagues will buy into. So part of this is quantitative analysis plus some just looking at item content and face validity and convincing your colleagues that you're onto something. And this is just a repeat of the goals of common factor model. So I mentioned earlier that there is a possibility of having higher order factor models. So what I was describing previously is known as a first order factor model. And that's where you might consider this, there are these factors that are identified by observed variables. So that's why they're first order. You've got observed variables, and then you've got latent variables one step up from the observed variables. But you can also have what are called second order factors, or even third or fourth or fifth order factors, but usually not ever above 3 that you see in the literature. There is a second order factor here is basically identified by 2 first order factors. So this is kind of twice removed from the observed variables. So second order in that sense. Just something to bear in mind. If you have a large item set, say you're going to work with 70 items or something, and you're going to perform a factor analysis, if you want to arrive at a model that fits well, you're often probably not going to be able to do it very often with a first order factor model. You often will need to have a second order factor structure, or possibly even higher than that, just because the interrelationships between the items is probably going to be more complicated than just the first order factor structure will allow. And it's best if you have a theory and a hypothesis at the outset. So you've got a set of items that you hypothesize represent a distinct set of latent variables, and you have very specific ideas about which items correspond to which latent variable. That's the best way to approach all of this. And if you were in that situation, then you would start by fitting a confirmatory factor analysis, and you wouldn't, at least initially, be interested in anything exploratory. But often what happens is the hypothesized measurement model isn't supported. You try it, but it doesn't fit well. And so then you're punting and you're trying to figure out if my hypothesis was incorrect, what might be a more reasonable measurement model for this set of items and responses. And sometimes there's just no a priori measurement model to test, and you just don't even have a good enough sense to hazard a hypothesis. So in that case, one option is exploratory factor analysis. And that's what I talked about last week, or a month, excuse me. But there's a lot of pitfalls with EFA in my experience. It can work, and it does work sometimes. For me, it works mostly when you've got fairly small item sets. If you start getting above 10 items or so, depends on the number of factors. And of course, if these are tried and true items that have been evaluated psychometrically and replicated multiple times, then you may have a very good idea of what the factor structure is, and it could be very clean and with items that are highly representative of the underlying factors. EFA can work very nicely there. But in a larger item set where there's a lot of exploration and uncertainty, I often find trouble with EFA. And it basically boils down to this simultaneous challenge. You're at the same time trying to figure out how many latent variables are represented by the items, and which, if any, of the items should just be removed from consideration. And as it turns out, that extraneous items, ones that should be removed but you haven't yet decided to remove, can kind of obfuscate the factor structure. But if the number of extracted factors is incorrect, then any important item can appear to be extraneous. So it gets very squishy. And if you're working with a very large item set, it can be really challenging. There's no rotation. There's literally unlimited, infinite number of rotation methods, literally. And I haven't found one that really works across the board. And one personal example, I worked with Anita Stewart years ago on an instrument that she developed known as the Interpersonal Processes of Care. It's basically questions, it asks patients about the communication style and the kind of the process of care with their primary care physician. We started with 79 items. I winnowed it down to 28, but it took over a year because of this issue, this simultaneous challenge. Working with that data set in the EFA framework was very, very, very next to impossible. It was almost completely intractable, and it took me forever. It's very frustrating for me, for the investigators. And this is before I knew about VARCLUS. I learned about VARCLUS years later, and I was really surprised what it could do. So part of what I'm going to do here is show you a reanalysis of the interpersonal processes of care. Okay, so what is VARCLUS? Technically, it's called oblique principal components cluster analysis. Where did it come from? Nobody knows, or at least no one is saying. You cannot find its origin anywhere. SAS has, it cites 3 references in the VARCLUS documentation, and none of them are about VARCLUS. But it does describe a little bit about what it is. It's a divisive method. It starts with all items in a single cluster, and then it goes through a bunch of steps. So it's just going to start dividing clusters. Excuse me. So in step 1, you identify the cluster with the largest second eigenvalue. So the largest second, if a cluster has a large second eigenvalue, it suggests that that cluster might have more than one dimension to it. And so if you find the cluster with the largest second eigenvalue, that's the cluster that's most ripe for splitting, basically. And the way it splits clusters is it just works with the particular cluster it wants to split. It's not working with the full item set. It's only working with the items in the cluster that's going to be split. It extracts 2 principal components from that set of items and then rotates them via raw oblique quartermax, which is probably a rotation method I never used in my life before. So if you think, so in the very beginning, all the items are in one cluster. And so it's really obvious which cluster is going to be split. It's going to be that one. So it just basically starts by extracting 2 principal components from all of the items in the total model and rotates them via raw quartermax. Then step 2, it kind of goes through this process where it just tries kind of moving items from the cluster it's originally assigned to other clusters, just to see if it can try to maximize the total amount of explained variation. And how it exactly does that is not completely clear. SAS provides one reference that says it's kind of related to a certain approach that someone else used a long time ago. But I think there's more to it than that, and there's some options there, but I just use the default. So then so now we have 2 clusters. And so as we go, we're going to move from having 2 clusters to splitting one of them to end up with 3 clusters. So what VARCLUS would do is look at the 2 clusters, figure out which of the 2 has the largest second eigenvalue. That cluster, say it was cluster number 2, would get split. And so there would be a new cluster 2, and a new cluster 3, both of which are subsets of the original cluster 2.
Excuse me, Steve, we have a quick question. How to define the largest second eigenvalue? Is there a rule of thumb? It
just looks across all the clusters, looks at the second eigenvalue across all the clusters, and will just choose the cluster that has the largest second eigenvalue. So it's just relative size across all of the clusters. Does that answer? Oh, there it is. So I'm not sure if that answered or not. I do have my chat up now. I didn't before.
Thank you.
So yeah, VARCLUS gives you options to kind of stop splitting clusters after, based upon a certain eigenvalue size and all of that. And I just don't even worry about that. So I just let it run. So back to the, we had 2 clusters. Then the next step is to find one of those clusters to split to form a 3 cluster solution. So again, VARCLUS is just looking at the 2 clusters, whichever one has the larger second eigenvalue, it's going to work with that set of items, not the whole set of items, but just the set of items, say from cluster 2. It's going to extract 2 principal components from the cluster 2 items, rotate them via Quartimax, and then that's going to, initially for step 1, you're going to have your original cluster 1, and then you're going to have your new cluster 2 and your new cluster 3, which are each subsets of the previous cluster 2. And then it's going to do the iterative reassignment of individual items, however it does that, just to see. And a lot of times that step 2 doesn't make any changes at all. Everything just kind of stays put. But occasionally an item or 2 moves around. And so you can check that by comparing the 2 cluster solution to the 3 cluster solution in many cases. So what happens here, so we've got like this, right now we've got this 3 cluster solution. The new cluster 2 and the new cluster 3 are definitely allowed to be correlated because the rotation method is oblique. So oblique means correlated. So after this oblique Quartimax rotation, the cluster 3 and the cluster 2 may be correlated. They can be correlated. There's no restriction on their level of correlation. And by virtue of the fact that the splitting of cluster 2 into the new cluster 2 and the new cluster 3 only focused on the items that were part of the original cluster 2, the new cluster 2 and the new cluster 3 can be correlated with cluster 1. So there's no kind of imposing orthogonal outcomes here. So all of these, so that's why up here it's called oblique principal components cluster analysis, because you end up with potentially correlated clusters. You just repeat these steps until the stopping rule is satisfied. And I always just set, as I'll talk about later, the stopping rule as with the max number of cluster that I'm interested in looking at. So I'm not looking at number of iterations or anything like that, or eigenvalue size. I just go with, I just ask for more clusters than I think I'm ever going to want. and then I look at those solutions to figure out where I want to land with it. So it's very subjective for me, but not completely. I did see that there are supposedly R and Python implementations of VARCLUS. I have no idea if they are really identical in every way to SAS VARCLUS or close or what, but I did see that they exist. So yeah, I said some of this already. Documentation is Spartan. If someone knows who wrote I mean, I think probably someone made VARCLUS and never put their name in the code or something, and people forgot. And I think people just don't know where it came from. I don't know. But if you do a PubMed search, there's only like 15 articles. There's more than that have used it because I don't think there's anything in Stata SD. But maybe there is. I didn't see it. I've published papers that use VARCLUS but didn't include the word VARCLUS in the abstract. So I know there's more than 15 out there, but there's very, very few. And most of it is not in medicine or behavioral science. It's often in other fields. So it's really simple to write VARCLUS code. It's like hardly takes anything at all. Basically, you have a variable list that's just the items that you want to cluster. If you tell it what your data set name is, I always ask it to work with the covariance matrix of the items and not the correlation matrix. So in a covariance matrix analysis, the items that have higher level of variation basically have more importance in the analysis, which makes sense because the more variation you have, assuming everything's measured on the same metric or the same scale, items with more variation include more information. And always set min clusters to 1. That's the minimum number of clusters. That's important. And then you set your max clusters value. And that's, for me, that's the stopping rule I use. I do use other options just to control the amount of output. And you can just choose those on your own. This is going to, so someone has a question about what kind of items you would include. Anything you'd be comfortable working with a correlation or covariance matrix. So, continuous, ordinal, with at least 4 categories, probably maybe 3 sometimes, but at least 4 or 5 most of the time for me. Binary would be a bad idea. If you're going to work with binary variables, you might consider tetracore correlations, but those have their own issues. They're noisy, so that can be an issue. So that's all there is to the code for VARCLUS. And so now I want to get into some examples. The CLV user written command, I'll have to look at. So this is a fairly early, it's not my first. The second example is my first use of VARCLUS. This is a fairly early one. It's a 42 item self-report measure of men who have sex with men in China, their stigma management strategies, and Wayne Stewart wrote this instrument as part of a project that he and Kyung Hee and I worked together on. It's been a while now. And so there was 150 respondents. These are Chinese MSM. And so an example item is to appear heterosexual. I sometimes talk about fictional dates with members of the opposite sex. And so there were 6 ordered response options. And so people would answer all 42 of these items. So I'm going to switch to the handout in a second. But before I do, I just want to say, mostly my goal is looking at I just look at the item labels in the output mostly. I'm looking for a kind of subjective, quote, purity of cluster content. But I do look at what's there's one column in the output called R² with own cluster. And these days, I like to see those values to be over 0.5. That's not hard and fast rule. If the item content is compelling, that's good enough for me. I don't pay too much attention to this R² with next closest cluster, or the 1 equals, or 1 minus R² ratio is what that's supposed to be, not equals. And VARCLUS also reports proportion of variance explained by the cluster. So overall, how much variation in the total data set do the clusters explain? And I like to see a value of about 0.7. And the reason for this is just because that seems to be about the place where, when I subsequently fit a confirmatory factor analysis model, it tends to fit well. So I'm going to switch now, and you may have to adjust your screen zoom rate again. Tor wrote a long note about the CLV, which I don't have time to read now. So this is, I'm going to go through several pages of SAS output here, and I hope everyone can see this, or you have the printout in front of you. So this is page 1 from the handout. And so I'm just starting with the 2 cluster solution. And you can see here at the top, total variation explained. Well, the proportion is 0.34, so about a third is explained with a 2 cluster solution. And if you look at the kind of item content here, the first cluster is kind of like a broad swath of different concepts related to being closeted or secretive about your sexual orientation. And the second cluster is kind of like a general outness cluster. So, but if you look closely at the item content, there's all kinds of different types of stigma management strategies that are represented within each of these clusters. And if you look at the R² with the own cluster, this is the one I tend to look at. There's, you know, a range of values from 0.1, you know, 0.12 here to 0.5, etc. And the similar kind of range here. And so just based upon looking at the item labels here, I'm not satisfied that this is really the stopping point that I'm interested in. And also this proportion is a little bit low. What it says here is cluster 1 will be split because it has the largest second eigenvalue, and it tells you what the eigenvalue is, the second eigenvalue of cluster 1. I don't worry if that even gets sometimes below 1. I don't worry about it. So if you look at, this is now the 3 cluster solution. So cluster 1 got split. And so for the most part, what was cluster 1 here is the new cluster 1 and the new cluster 3. So that's what got split. Cluster 2 is pretty much going to be the same as it was before, and maybe it's exactly the same here. I didn't check item for item. The only reason why it might not be different is if in the step 2 of VARCLUS, where it checks to see if moving individual items around might improve the overall explained variation of the cluster solution. So it's possible that something could have moved in or out of cluster 2 in this solution.
So Steve, I couldn't follow this because the number of items in each cluster changed.
Well, like I said, there's, I don't know how many items are here in cluster 2.
Well, it lists it, right?
Well, here's cluster 2 again.
No, up below it tells you members, right? So it tells you the number of items in each of them, right?
17 and 19, right? So cluster 2 must have experienced some departures based upon the step 2. So this, so step 1.
38 and 42.
Sorry.
38 and 42.
Oh, okay. Yeah, thank you. So in step one of VARCLUS is to split cluster 1 into 2 clusters. And then step 2 of the forming the 3 cluster solution is to kind of check whether moving items around might improve the proportion of variance explained. So apparently 2 of the items that were originally in cluster 2, the cluster that was not split, but in step 2 of the VARCLUS kind of iteration, 2 of those items, as Lance mentioned, got moved to other clusters.
Okay, thanks. That was confusing to me. Yeah,
Okay.
because I thought the second item is not being touched.
Right.
Yeah.
It's not in step 1, but potentially all clusters are potentially going to be modified in step 2. So now the cluster 1, what was cluster 1 has been split. And so the new cluster 1 is kind of focused on avoiding certain kinds of social situations and kind of just being silent in others. And this cluster 3, which used to be part of the previous cluster 1, is kind of related to concepts of counterfeiting, trying to pretend that you're straight, things like that. So it makes sense that those kinds of that 1 and 2 or 1 and 3 are different, and the proportion explained variation went up a little bit, and then it tells you that cluster 2 is going to be split because it now has the second largest eigenvalue. And so if we click down here, basically what was cluster 2 is a combination of cluster 2 and cluster 4 here. Again, in the step 2 of the process, there could be some kind of jiggling of items around. And so what the new cluster 2 is kind of, if I were to try to say something rough about it, it might be like actively informing others that you are gay. It's not every single one of them is not so active. And the 4th one is maybe more of kind of, it's really to confrontation, confronting others about homophobia and things like that, and also some support related items. And so we can keep going here. We're at 0.46. There's still some kind of low R squares with own cluster, and maybe some, looking at item content, there might seem to be some within cluster heterogeneity. So down here it says cluster 1 will be split. And so here we have the 5 cluster solution. So what was cluster 1 is mostly what's now cluster 1 and what's in cluster 5. This cluster 1 has to do with kind of silence and withdrawal. And cluster 5 seems to be more like active avoidance. So you just keep going through this process. And I'll show you where I ended up. I ended up with 16 clusters because I just kept going. And this led me to a kind of level of content purity that I was reasonably happy with within each cluster. And I've reordered these clusters now because subsequent to the VARCLUS analysis, I conducted, I think I did a VARCLUS of a VARCLUS. So you can, with VARCLUS, you can get your 16 item solution. You can ask VARCLUS to output the correlation matrix, the intercluster correlation matrix. So you've got this 16 by 16 correlation matrix that you can then input into a second VARCLUS run if you want to, or into EFA. Or you could create like composite scores for each of these clusters and then input those composite scores into a second VARCLUS run or an EFA run to try to understand the second order factor structure here, because you probably don't want to have 16 scales unless you have, you're going to pick and choose a subset of them for some specified reasons. If you want a general use instrument, you would hope that there might be a higher order structure so that you could have something more parsimonious than 16 different scales. And so I did, going the wrong way, this is a second order VARCLUS. So I can't remember how I did it. I either input the correlation matrix from the first VARCLUS into a second VARCLUS or use the scale scores. But I obtained these second order clusters of clusters, basically. And these are the numbers for the first order clusters, and it's not very clear here because these are just numbers and they don't have labels. But if we go back here, we can see these are the second order cluster labels that I just put, that I adopted for these. So there's like 5 first order clusters here that are in this kind of avoidance higher order cluster, and then there's 4 first order clusters here that are kind of related to outness, and there's 4 first order clusters here related to counterfeiting, and then there's these smaller, this is just a single cluster, first order cluster that's not combined with any other cluster that relates to family and parents, and these 2 clusters are support related. So that's kind of just an example of how you can move through an analysis like this. So that's my end of the first example. I should go back now to the slides. No, wrong one. So one of the things I want to emphasize is that you really want, with VARCLUS, for me anyway, because I am mostly interested in the item content when making decisions about what constitutes a good solution. You really need detailed variable labels that capture the kind of subtleties and the essence of the items. You don't want to have just these superficial labels. And so I tried, and and you also want to make them fit on the page, so you just have to be creative, but you really want to get all the nuance in there to try to understand whether or not you've got content purity. This was a pretty unusual example because all 42 items were retained in the final solution. So some of this just is attesting to Wayne Stewart's skill at creating instruments. because he's very meticulous and careful about it. And I did want to point out that, you know, in the first part of the example, we kind of walked through the 2 cluster, 3, 4, and 5 cluster solution, but then jumped forward to the 16 cluster solution that had a 5 second order cluster kind of way of summarizing it. Those 5 second order clusters are not the same as the 5 cluster solution. So just be aware that sometimes you really need to kind of end up with these more micro clusters that you then aggregate back up to a higher level of abstraction. If you try to shortcut that by just asking for 5 clusters initially, you may not get the same answer. And probably if you tried to fit a confirmatory factor analysis of the 5 cluster solution, it wouldn't fit as well as the 16 cluster first order cluster with a 5 second order cluster solution. Okay, here's the second example. This is the first time I ever used VARCLUS. And so some of the results here, I wouldn't, if I were to do this today, I would probably do it a little bit differently. But this is the project where I was like blown away by, for the first time, about how well VARCLUS worked. So Jean Tachon was a colleague of mine in psychiatry for many years. Some of you probably know her. She developed this 68-item self-report measure of Latino parents' child feeding practices. And so this study had recruited children and their parents, and then interviewed moms and dads. And so one of the things that Jean wanted to do was to understand whether mothers and fathers thought of child feeding practices in the same way. And not only that, but how do their child feeding practices affect their child's health, et cetera. So there's these 68 items. An example item is, how often do you let your child eat whatever he or she wants? And then they have these 5 ordered response options. So just for some background, the analysis plan was to stack the mom and dad's data to just so that we had, you know, putting everyone's data together and ignoring the kind of correlation between individuals within a couple, just to understand the exploratory, use an exploratory approach to understand the factor structure of this 68-item instrument. Once we obtained kind of a VARCLUS solution, then the idea was to kind of reshape the data to represent 174 couples and fit these first order factor models that would test whether the factor structure for mothers and the factor structure for fathers were equivalent. And this included a lot of tests to see if the meaning of each of the factors was the same across mothers and fathers, and whether the scaling of their responses would allow for a direct comparison of, say, you know, mothers' feeding practices versus fathers' feeding practices. If you took the difference in some scale scores, would that represent a difference in the construct of interest, or was it contaminated by some kind of response biases, et cetera? And again, exploring the second order factor structure because there were a lot of first order clusters. And so some further probing of CFA. I don't want to get into the CFA too much, but just to give an idea of where we're going with all of this. So I'm going to switch now. Oops. So I'm just jumping straight to the 14 cluster solution, which is what I selected at the time. one of the things I'll point out, you'll see there's like some of these R squares with their own cluster are below 0.5, some of them well below 0.5. I'm not saying that I would definitely keep looking for another solution, having seen those kinds of coefficients, but I might these days. Whereas at this point, I might have been happy enough with this solution. So I would definitely look further these days, but I still might revert back to this solution based upon those coefficients, because it suggests that some of these items maybe either are singleton items or maybe would end up joining with another item in a smaller cluster that's more specific if I extracted more factors. But I want to, this is just 12 of 14 clusters. So what I did is I chose a 14 cluster solution, and then I tried to find a second order factor structure of the of those 14 clusters, and it became very complicated. And I found that to kind of simplify the second order structure, I really needed to get rid of 2 of the first order factors. And this is a situation where when exploring the second order structure of things, VARCLUS can not do a very good job, because VARCLUS is happy when everything kind of belongs to one cluster. And so in the second order, if I've got 14 clusters and I'm trying to cluster them into a smaller set of higher order clusters, if any of those 14 clusters have complex relationships with the higher order clusters, if they want to be, if they are correlated with fairly strongly with more than one higher order cluster, then VARCLUS will have a problem giving you a simple answer in that case. Whereas exploratory factor analysis is better able to accommodate that kind of complexity. So in this case, these are the 2 of the 14 clusters that were excluded from the second order, eventually from the second order structure model. And these are the 12 that were retained. And so these are some labels that I added to represent the kind of overarching construct or idea of the second order factor that's represented by each of these corresponding first order clusters. Some of these are crossed out, and that's because some of the items were dropped. I think this item 23 was dropped in the process of doing the VARCLUS analysis. So just because of content alone, this is withholding sweets from your child for bad behavior. It's just not an item that's well, the whole idea of this concept here is not well represented by other items, because this is like punishment of a treat for punishment for bad behavior by withholding something. And there's just not a lot of other items that are along. There are other kind of punishment items, but not quite of this type. So I think I would often expect that if I extracted more factors or clusters, excuse me, that this might end up as a singleton item. And perhaps it would have if I kept going. But again, this was my first use of VARCLUS, and so maybe I stopped a little bit sooner than I would these days. These other items were dropped as part of the CFA, so I think fitting a confirmatory factor analysis model, I found that the factor loadings, the correlation between the item and its corresponding factor were probably kind of low, and so that's why those were dropped. So I don't have a problem dropping items. at all. And the next example, you'll see that a lot of items got dropped. And so basically what I did was I fit this 14 cluster VARCLUS model. I chose that one. I explored the second order structure. I dropped this cluster 8 and 11 and ended up with these 4 second order clusters of the 12 first order clusters. Did I go the wrong way? And so then I started fitting confirmatory factor analysis models. Now, as I said earlier, I dropped 3 items. 2 got dropped in because of decisions made during VARCLUS. 3 got dropped during CFA. So we're talking about 60, I can't even forget. It's been so long. Yeah. Oh yeah. So I'm dropping 5 items out of well over 60, which is pretty good. VARCLUS tends to retain more items than would be the case when you're using EFA, I have found. And so that's a real advantage of VARCLUS. And then I was telling you about these kind of complex models that we're testing in variance of parameters across mothers and fathers, and you know, just testing to see whether or not the factor structure was equivalent across mothers and fathers. And so other than dropping the 3 items from the CFA, there were no other changes to the analysis plan when it comes to the confirmatory factor analysis. And so these, what are calling strict invariance, that is holding, so for every corresponding parameter for across mothers and fathers, so each corresponding factor loading, each corresponding item residual variance, each corresponding item intercept, the factor variances, the factor covariances, every single corresponding parameter estimate for mothers was held to be equivalent or equal for fathers. So this is a highly constrained model with a lot of equality constraints. And anyone who's used to working with confirmatory factor analysis will look at these RMSEA values. Usually anything below 0.05 is considered good. And CFI, anything above 0.95 is considered good in terms of model fit. These models, considering it's 60 items, basically, with clustered, you know, participants, comparing invariance of parameters across those couple members to get fit like this, kind of straight off of exploratory factor analysis or exploratory kind of analysis to explore and understand the latent structure is really unheard of. And I would never get this result if I was using EFA alone, I guarantee you. So that's, I think, the last for that particular example. Yeah, so I had 63 of 68 items. I tried EFA first. I was able to retain about 50 items, but I didn't even move on to CFA after that because I think I was also pretty unsatisfied with the solution in general in terms of the content of the factors or item clusters. So that's below is a paper that describes the results more fully if anyone's interested. It's got an appendix where most of the details are, but it probably doesn't. It's probably talking more about confirmatory factor analysis than it is about VARCLUS. So it's probably not a very good resource for VARCLUS. And so then the third and final example is interpersonal processes of care. Started out as a 79-item patient report measure. This is Anita Stewart's work. There was 1,600 patients from 4 racial, ethnic, and language groups. And the idea was to test for invariance of the factor solution across the 4 groups. And we did do that. But this example doesn't get into that. This is an example I mentioned earlier where there was an EFA I was working on for years, and I ended up with like 29 of 79 items at the end of the day, and we published on that. But then years later, I learned about VARCLUS and came back to do a reanalysis of the data, and so we'll see. So yeah. I basically said all of this, 12 first order factors with 29 items and 7 second order factors, and was published in Health Services Research. That's before I knew about VARCLUS. And so the new analysis plan was just to look at, you know, can I get a better factor structure with VARCLUS, retain more items, and explore the first and second order structure of things. So I'm going to switch now to this. And so I extracted 31 clusters from this out of 79 items. And there was a lot of singleton items. So here, all of these were singleton items in the 31 cluster solution. And I just dropped them. And then going the wrong way again, there's this item I just dropped because I didn't think the content was right for that cluster, so I just dropped it. But you can see, you know, multiple clusters within each second order cluster, and you can kind of look at this and ponder the content if you like. I don't want to go into too much detail on it. And then there was this last cluster that was part of the second order model. So again, I tried to fit, I started with these 31 clusters. I got rid of all of these singleton clusters. And then the remaining clusters, I tried to explore the second order cluster with a second VARCLUS analysis. So basically inputting the correlation matrix from the first VARCLUS solution into a second run of VARCLUS. Or maybe I I created scale scores first and then input those into the second VARCLUS. And it was kind of not making a lot of sense. So I think I ended up using EFA again, because I think the relationships between the first order and second order clusters or factors was complicated, and EFA did a better job. And in the process, I dropped these 2 first order clusters from the second order model. And so this shows the EFA of the first order clusters and how they map onto the 4 second order clusters. And these are the kind of same labels that were on the previous page, going up here, these and this. So this just shows the kind of second order structure of this. And so I then fit some confirmatory factor analysis models of the 18 first order factors, and this is the fit I got here. This is very good. And also this second order model with the 16 first order factors, the fit's very good. So this is with no modifications. Once I used VARCLUS to obtain the first order clusters, and then EFA to figure out what the second order structure was, I just moved immediately to fitting CFA models and got a really good fit. So going back to the slides. So that analysis, starting from first execution of VARCLUS to two well-fitting CFA models, starting with 79 items. And yeah, I got rid of quite a few of them, but I still had a whole lot more items at the end of the day retained than 29 from the original analysis. This took me, it was less than an afternoon. The original analysis with EFA took me more than a year, and I was not working on it every day, all day long or anything like that, but because I got so frustrated with it, I would put it down. But it really took a long time, and it was an okay result, but it's not nearly as good or as promising as this result is. And so it's, to me, it's like an example of how VARCLUS can be vastly superior to EFA for this kind of work. Okay. So that's the end of the examples, and we're almost out of time. But I just want to make a few more points. So this first thing, this is what I call a true implementation of VARCLUS. It starts with one cluster. You don't start with 5 clusters. You start with one cluster always. You don't have to, but I mean, that's what I think what you want to do. And then, but if you just said 16 and 16, what you're really getting is 16 principal components with a raw oblique quartermax rotation. That's what you're getting. That's not a VARCLUS solution. If you have continuous or ordinal variables, I would consider a Blom transformation or some kind of normalizing transformation prior to using PROC VARCLUS. You don't have to, but I think you might get a better result. And I usually use Blom just because it kind of rescales everything into a nonsense metric, but you're mostly talking about, in this context, standardized relationships between observed and eventually in a CFA factors. And so it kind of doesn't matter because a lot of what's reported is often standardized anyway. And for VARCLUS, it doesn't matter because everything reported in VARCLUS, pretty much, not everything, but most things are pretty standardized. So that's okay. I just tried to see if I could get the same result from VARCLUS and PROC factor if I kind of tweaked the right options. So basically what I'm trying to do here is use PROC factor to get a raw oblique quartermax rotation of principal components where there's 2 of them, and have VARCLUS do the same thing. And I figured out that if I use max search equals 0, max iter equal 1, that it's basically going to give me the same thing as PROC factor in this case. That just helped me to understand, assured me to understand that I kind of actually knew a little bit about what VARCLUS was doing under the hood. So in summary, VARCLUS includes some helpful statistics. R-square with own cluster is what I look at. I don't really look at R-square with next closest cluster. But proportion of variance explained, the proportion of total variation that all of the clusters explain, I think is important. Again, I think that around 0.7 or higher is where you're getting in the territory of a CFA might support what you've got from VARCLUS. When I'm saying those are useful, I mean these up here are useful, but subjective judgment I think is the best initial guide. You should really be looking for content purity. I don't worry about singleton clusters. If they look like singletons, I just drop them. And the nice thing about VARCLUS is you don't need to drop them from the variable list in the analysis. VARCLUS just kind of spits them out as singleton clusters, and they don't perturb anything else anymore. In factor analysis, you have to kind of get rid of items. Otherwise, they perturb everything. And that's another reason why I like VARCLUS. It's just a lot more robust to that kind of circumstance. And yeah, if I don't like an item, I just get rid of it. It's exploratory. So again, VARCLUS I think is a whole lot better for large item sets, for first order factors or first order clusters. And how well it works to identify second order factors or clusters kind of depends upon how complex the relationships are between the second and first order factors. If they get complex, it's better to kind of use EFA to explore that second order structure. I use covariances as input, not correlations. And just because I think that's a better approach, and experiences conceptually as well as experience has shown that I think it produces better results. And even though subjective judgment is a big part of this process, I really, myself personally, like to fit a confirmatory factor analysis after the VARCLUS. I think it helps to sell the result scientifically because VARCLUS isn't well known and it doesn't really have any kind of definitive tests of model fit. And CFA is fairly well known and has a whole kind of battery of diagnostics. So it's a good complementary approach to use. And I'll just say that every time I use VARCLUS with a large item set, when I pick the VARCLUS solution that I'm happy with, and then I go to fit a CFA, I've had very good results. And I can tell you that probably never when I used EFA and moved to CFA did I have a very good result without some major modification on the CFA side of things. So it's kind of night and day from my perspective. And again, VARCLUS tends to retain more items than EFA does, at least in my experience. So it's another big plus for VARCLUS. And again, subjective judgment is really key. So I think every user of VARCLUS might have, a different style with it because I think subjective judgment is a big part of it. But I really encourage people to try. If you've got a large item set, try VARCLUS first. Yeah, and like I said, I used to be scared to work on large item sets because you kind of get married to this project that might not ever have there's no way to predict how long you're going to be at it, and it could be a very long time. But with VARCLUS, I can basically know that I'm going to be working through it as fast as any analysis could be conducted. So I'm really happy with it. And that's it. We're almost completely out of time. Thank you very much.
Yay.
Thank you.
I don't think there's any questions.
Yeah, I can say something like Mr. Neyman, Jersey Neyman used to say, life is complicated, but not uninteresting. He liked to talk in double negation. Anyway, that was phenomenal, really. Thank you very much. And to let people know, let's thank the speaker virtually or otherwise. Yes. And the slides will be posted on the Method Core website soon, so we can look at them. This was amazing. Are you sure you don't want to do it anymore?
Well, you know, I don't know what I get to do these days. It's more shelter in place, perhaps. I don't know, but
Right, right.
Quick
Thank
question.
you. Yeah.
I have a quick question. Great presentation, Steve. I really appreciate it. And congratulations on your impending retirement. As a brief note, I recently retired from UCSF. So that's myself. So that's good. 13 years there with you guys. Now, have you tried something like machine learning to do something that the clustering analysis is doing as well, to kind of look at the performance differences? So, XGBoost or something in R.
Yeah, I mean, I personally haven't, and I was just looking at like, current issue of Psychometrica, and someone has done some kind of artificial intelligence application in kind of exploratory factor analysis kind of vein. I didn't read the article yet, but that could be a whole area that is really going to put EFA, on the back burner, because people keep trying to perfect it, and it really needs a kind of a shift, I think, in perspective to kind of move forward. And so, yeah, I don't know anything about those, but it's interesting. But I gotta say, VARCLUS works amazingly well, in my judgment. So I don't know if you could get any better. Maybe you can, but I don't know if you could. I mean, if you could have something that automatically would do like higher order structures, that would be cool.
And possibly if you have a lot of data, a lot of variables, very high dimensional, then maybe
Yeah.
so that maybe VARCLUS is still useful, but it might choke, whereas the machine learning might be better, but that's to be seen.
Yeah, I mean, I imagine that it would still need to be supervised at some level, because there's always going to be, unless you have a huge sample, there's always just going to be some sampling variation that kind of throws items in the wrong place, so to speak, or nonsense kind of pairings of items based upon their content. But yeah, I'm sure that's an area that's really going to take off.
Thank you.
Sure. Yeah, I mean, it's kind of too bad because for the EFA talk, there was a lot more participants, and I consider this talk to be a lot more important than the EFA talk.
It is, but hopefully people will look at the website.
Yeah, hopefully.
Yeah.
But it's yeah, I don't know if I scared people away, or people just are interested in EFA, but yeah, I use EFA very sparingly these days.
Yeah. Anyway, did everybody fill the questionnaire?
Yes.
Good. Thank you, Steve.